Continuing on with Unit 7, this is Learning Target 7b, which is all about radicals and rational exponents. By the end of this lesson, you will be able to evaluate radicals to simplify expressions, rewrite exponents in radical form, and rewrite radicals in exponential form. So let's start with what a radical expression is, and let's talk about all the pieces. So in this radical expression we have three things. The n, which is a superscript in front of the radical sign, is what we call the index. That tells us what type of radical we have, if we have a square root, cube root, fourth root, fifth root, or etc. The radical symbol here is this guy, which I'm going to trace for you guys in purple. That's what we call our radical sign. And then whatever's underneath that radical sign is what we call the radicand. So in this example, our A is our radicand. Now that radicand could be a single variable, or it could be a combination of a coefficient and a variable, so one single term. Let's talk about how we would pronounce this. So how we would pronounce this is we would say that this is the nth root of A. So remember, our index is n. So if I were to have an index here that was a 5, for instance, we would say that's the fifth root of A. So that n is going to take on any numerical number that is greater than or equal to 2. So n is going to be an integer value that is greater than or equal to 2. And the index gives us the degree of that root. There is one special case where we wouldn't write a number, and that would be when we would assume that the index is 2. So you guys might have seen square roots before, where we don't write the 2. So if I see a radical sign without any number in the superscript in front, we assume that that number is a 2, and it is called a square root. So in this example right here, we would have the square root of A. Now, the square root has a special term. So if our index is 2, we call it a square root, but the same thing holds true if our index is 3, we would call that a cube root. Now, if the index is 4 or higher, we would call that a fourth root. So if the index is 4, we'll call it a fourth root. If the index is 5, we'll call it a fifth root. If the index is 100, we call it the 100th root of it. So for any index values that are 4 or higher, we just refer to it as the nth root, where that n is that number value. So let's think back to our pre-algebra courses. We know that 5 squared, so this 5 to the 2 exponents are 5 squared, is equal to 5 times 5, which would give us 25. That in turn is the reason why the square root of 25 is going to be equal to 5. So I can rewrite the 25 as 5 to the second power, and then the key thing here is that the square and the square root cancel each other out. So what we're looking for is our index to match our exponent, and they will cancel each other out. And this happens for any index. This could happen for a cube root. So if I have the cube root of, let's say, 5 to the third, then if that index, let me make sure that looks like an index written. So if I have the cube root of 5 to the third, because the index here matches the exponent, they would cancel each other out, and we would end up with just the base, which would be 5 in this example. We could do this for any root. So let's say I have the 7th root of, let's say, 10 to the 7th. That would be equal to just 10, because the index is matching the exponent, so they cancel each other out. Now, that doesn't perfectly happen every time, and what we're going to look at is some examples where the index doesn't perfectly match the square root, perfectly match the exponent. Maybe there's some extra things there as well. One thing that's going to come in handy for us is we're going to draw a factor tree so that we can figure out what all the factors are and help group them together so that they help for that problem. So our goal is to simplify all of the radicals, and we'll rewrite the radicand. So remember, the radicand is the stuff that is inside the radical sign. So that radicand is the stuff that's underneath the radical. And we're going to rewrite that as a base where hopefully the exponent can match the index. Let's look at a couple examples. So our first example here, how would you pronounce that? So think about how you would pronounce what this says that I just underlined. We would say that this is the square root of 36. So in this example, our index is equal to 2 because there's no superscript written, so we assume that it's a 2. So I have what we call a square root. So we would pronounce this as the square root of 36. Now it might seem silly that I'm writing that out, but it's important to be able to read what the mathematical notation says on the paper, otherwise we won't be able to answer the question. And as they get a little bit more challenging, we want to make sure we're understanding all the pieces to it. So we have a square root because our index is 2, and we call it the square root of 36 because 36 is inside our radical, so 36 is our radicand. Now on the side over here, I'm going to do a factor tree on 36, which some of you might be thinking in your head, well, we know what the square root of 36 is. That's going to be equal to 6. Oops. Which I agree with you guys, but let's think through the process on why, so when we get to a little bit more complicated examples, we can see where all these moving pieces are coming from. So 36 can factor into 6 times 6, so I could rewrite 36 as 6 squared. What that tells me then is the square root of 36 can be rewritten as the square root of 6 squared, and because our index, which is 2, matches our exponent, they cancel each other out, and we end up with just 6. So this is one of those cases where we had a perfect square here because 36 is written as 6 squared, so it is a perfect square. Okay, let's look at our second example. What would your index be in example 2? Our index in example 2 is going to be 3. Remember, it's that superscript that's up there that we're looking for. So for this to be able to cancel out, we would want it to have an exponent of 3. So let's do a factor tree on 125 because that got to be quite a much larger number than 36. The first thing I think of is I can factor 125 is divisible by 5, and 5 goes in 25 times. And then 25 can be factored into 5 times 5. Now I can't factor any further because 5 is a prime number, but when I look at all the factors of it, I end up getting 1, 2, 3 of them. So 125 is equal to 5 to the third power. So I could rewrite the 125 as 5 to the third, remembering though that this is still all inside this radical. Now what kind of radical is this? How would you have pronounced the original problem? Well, we would say that this is the cube root, since our index is 3, of 125. Now that we've rewritten 125 as 5 to the third, this is one of those nice cases where the index and the exponent are equal to each other, so they cancel each other out, and we just get left with 5, which was our base. Let's look at our third example here. So why don't you guys pause the video and decide on what your index is on example 3. So in example 3, our index is going to be 4, since that's our superscript in front of the radical sign. So our goal would try to be to get an exponent that would be a 4. If I go write a factor tree, why don't you guys create a factor tree for 16 and then we'll check it together. So 16 can factor as 4 times 4. You could also do 2 times 8. Either way, you're going to end up getting 4 2s. Because when I break them all apart, we end up with 1, 2, 3, 4 2s. So I could rewrite 16 as, oops, not 4, as 2 to the 4th power. There we go. Which means over here, I could rewrite this as the 4th root of 2 to the 4th. So because our index is 4, we would call this the 4th root of 16 in this case. And we're replacing 16 with 2 to the 4th based off of our factor tree. Then the 4th root and the 4th exponent can cancel each other out, and we end up with 2. So our first three examples here worked out very nicely, where each one of those numbers inside of our radical, so each one of our radicands, could be rewritten as a power where the exponent matched the index perfectly. Let's look at our fourth example and see if that happens. So what would our index be on example 4? Our index here is going to be 3, so we have a cube root, and in this case we have the cubed root of 27. If we go draw a factor tree on the side, why don't you guys create your own factor tree and then we'll check it together. So we could factor 27 as 3 times 9, and then factor 9 as 3 times 3. So at the end of my factor tree, I have 3 3's, so 27 would be equivalent to 3 to the third power. So going back to our original problem, I could rewrite the cube root of 27 as the cube root of 3 to the third. In this example, it works out again that our index matches our exponent, so those guys will cancel each other out and we'll just get left with 3, where the 3 we're left with is the base. So there's quite a few 3's going on in this problem, but we're left with the base, which is 3. So in those first 4 examples, we saw all those cases where the radical completely disappeared, since we were able to rewrite the radicand, or the stuff inside the radical, as an exponent where the exponent matched the index perfectly. Let's look at example 5. What is your index in example 5? Our index in this fifth example is going to be equal to 2. Remember, anytime there's not one written, we assume that means that it is a square root, and so our index is 2. So I have the square root of 12. Let's go create a factor tree for 12. So when I factor 12, one way I could do it was I'll go 4 times 3. Then 4 can keep factoring as 2 times 2. 3 is a prime number, so I cannot factor that any further. Now this is the first example where we're seeing where all of our factors are not the same. So I have 2 2's, so I could rewrite 12 as 2 to the second times 3 then, because we can't forget about our other factor, it is still part of that number. So 12 can be rewritten as our 2 squared from our 2 2's over here, and then times our 3. Well, since 12 is equal to that, then I can rewrite this problem as the square root of 2 to the second times 3, since 12 was equal to 2 squared times 3. Now from here, when we look at this, part of this matches, and then part of it is kind of a problem. So on this first piece with the 2 squared, my index matches my exponent perfectly. But on the 3, that doesn't happen. Well, when I have multiplication inside of a square root, or a cubed root, or a fourth root, or any radical, I can break that apart into each piece. And in this case, take the square root of 2 squared times the square root of 3 separately. Now we have the piece that works out perfectly. So the square root of 2 squared, the index and the exponent match. So those guys will cancel each other out, and I'll just get left with a 2, because the radical and the square root are canceling. And then the square root of 3, I can't simplify. It's not a perfect square. I am stuck with just the square root of 3. Our final answer is then going to be 2 times the square root of 3. And the reason they're being multiplied here is because in our factor tree, I ended up with 2 squared times 3. So although we simplified the square root of 2 squared part, I'm still multiplying it to the kind of extra stuff that didn't simplify all the way, which was the square root of 3. So there is our first example where not all the time are we going to simplify this all the way and get rid of a radical, but this is as far as we can simplify this example without a calculator. And we are not using a calculator in this section, so we have to be able to do these all by hand. Let's look at example 6. What is our index going to be on example 6? Our index in this case will be 2 again. So I have another square root, and I have the square root of 20 this time. Why don't you guys create a factor tree for 20 over on the side, and then we'll check it together. So 20 can factor as 4 times 5 would be one option, and then 4 could factor as 2 times 2. Now, from the beginning, you could have gone 2 times 10, and then continued to factor 10 more, but in the end, we're going to end up with 2 2's and a single 5. So this is similar to our example 5 that we had. We ended up with a pair of something, so we ended up with 2 squared, then times this extra 5. What that means is in my original square root, instead of taking the square root of 20, I can replace the 20 with 2 to the second times 5. From here, it's going to be similar to an example 5. Now, I think you guys should pause the video and try to finish example 6 on your own first, and then we'll check it together. Okay, let's finish checking example 6. So once we did our factor tree, we were able to break 20 apart into 2 squared times 5. The 2 squared is a perfect square, so I can rewrite this as the square root of 2 squared times the square root of 5. From here, the square root of 2 squared will simplify down to be 2, since the square root and the square cancel. And then the square root of 5 is unfortunately stuck. It's as simplified as it can be, so I end up with 2 times the square root of 5 as my final answer. Okay. So in those last two examples, we saw what would happen if we didn't end up getting rid of the square root all the way, and that definitely can happen. In fact, it happens more times than not. Let's look at example 7. So we have, it says simplify the cube root of 16. So in this case, we have a cubed root. What would our index be then? Our index is going to be 3 since we have a cubed root, so we have that 3 as a superscript. Let's go off to the side and factor 16, just so we can get it down to its prime factors. So 16 can factor as 4 times 4, and then the 4's can keep factoring as 2 times 2, and then 2 times 2. In the end, we ended up with 4 2's. So 4 2's, so we would end up with 2 to the 4th. Now, my goal was to get the exponent to match the index. My index is 3, so they're not matching, but I can make them match if I instead just group 3 of the 2's together and then keep the extra 2 out on its own. So I could rewrite 2 to the 4th as 2 to the 3rd times 2 to the 1st. We also know we can do this because based off of Learning Target 7a, one of the properties of exponents said if I multiply 2 exponents with the same base, I would then add the exponents. Or if I multiply 2 powers with the same base, I'd add the exponents. So 3 plus 1 is how we got back to the 4. What we're looking at is we're trying to group it so it's in groups that equal the index. So because my index is 3 here, I want to group these in groups of 3 together. So I was able to create one group of 3, and then I have something extra, which is similar to what happened in example 5 and 6. So if I rewrite this now, I could rewrite the 16 as 2 to the 3rd times 2. Again, I want to break this apart. So I end up with the cube root of 2 to the 3rd times the cube root of the 2 to the 1st. I'm going to draw a line there so we're not getting the factor tree in our work mixed up. But we're able to do this because 16 can be factored into 2 to the 3rd times 2, and then we broke apart the cube root from there. On this first piece with the cubed root of 2 to the 3rd, the index and the power and the index and the exponent match, so they can cancel each other out, and we end up with 2. Now the cube root of 2 can't simplify any further, so I'm going to just rewrite it, and we end up with 2 times the cube root of 2. And I will put parentheses here just so that it's clear that the 3 is the index, and we don't accidentally make it look like an exponent on the coefficient in front. So the 3 is the index still on our radical. So example 7 was similar to 5 and 6 because there's still a radical left. The difference here was that, yes, it can factor down to be all the same factors, but we have to make sure we're grouping them based off of the number in our index. Okay, example 8. So again, I have an index of 3. So I have another cube root. This would be the cube root of 128 now. So we got quite a bigger number, but that's okay. We can still do a factor tree on it. So I'm going to do the factor tree over here on this side. So 128, well, I know it's divisible by 2 since it's an even number, so I'm going to go 2 and 64. Since 2 times 64 is 128. Then from there, I'm going to just keep factoring with 2's. So I end up with 2 times 32, and then 32 can factor as 2 times 16. Probably going to need a little bit more space. And then 16 can factor as 2 times 8, and then 8 can factor as 2 times 4, and then the 4 I can keep factoring, wow, as 2 times 2. So I ended up with 1, 2, 3, 4, 5, 6, 7 2's. Wow. So 128 is equal to 2 to the 7th. Remember, our goal is to have these grouped, the 2's, grouped based off of the index. So I want to group them in groups of 3. So if I start highlighting these in groups of 3, I've got 3 of them right there. So that will be a 2 to the 3rd. Then I could do another 3 of them. Let's use green. I'll use that 1, 2, and 3 there. And then I have an extra one left over. So I have 2 to the 3rd times 2 to the 3rd times a 2 to the 1st. And that's okay. We saw what happened in example 7 when we had an extra left over too. But in this example, it just so happens that we actually have 2 of them that we can group together in groups of 3. So I can now rewrite the cube root of 128 as 2 to the 3rd times 2 to the 3rd times our 2. I can break this apart as the cube root of 2 to the 3rd times another cube root of 2 to the 3rd, since there's 2 underneath the radical, times the cube root of 2. We know that if the index and the power match, then those guys will cancel each other out and we just get left with our base. So I get left with 2 there. Again, the index and the exponent match, so I just get left with my base, which is 2. And then the cube root of 2 I can't simplify anymore, so I'm going to just multiply it and bring it down. I can simplify this a little bit more since 2 times 2 is 4, and I end up with 4 times the cube root of 2. Again, I am putting parentheses around it just so that it's clear that this 3 is the index and not accidentally looking like an exponent on the 4. So as we can see through these examples, we do have some numbers that can perfectly simplify inside of square roots. And that happens when, well, if we have a square root, if it's a perfect square, if we have a cube root, that will happen if it's a perfect cube, etc. And if we have numbers that are not perfect squares or perfect cubes, that's okay. We can break them apart on a factor tree and group factors together that will end up canceling out and leave the extra stuff still inside the radical. Okay, now you might be wondering, well, in our last section, we talked all about exponent rules, and now we're looking at radicals. I can see that we're bringing exponents back, but really, how do those connect? Well, radicals and exponents are actually 2 different ways to write something. So we can have a radical form. So we have a radical form over here on the left that says the nth root of a. That is equal to this exponential form that says a to the 1 over n exponent. So we can go from a radical form to an exponential form by rewriting the index as a fractional exponent. So over here, our n, remember, is our index. Over here in exponential form, our index is still there. It's just the denominator of our exponent. So this a to the 1 over n, just to make sure we're clear, the 1 over n is the entire exponent, and that index is the denominator of that exponent. So that's really handy for us to be able to go back and forth between these two, which is actually another way to prove what statement we had earlier. So if I go back to the problem that said the square root of 36, remember we rewrote 36 as 6 to the 2nd, then we still had the square root, but from here, if this is a square root, it means my index is equal to 2. So I could rewrite this in exponential form, and we're going to see really why the square root and the square cancel. So to rewrite this in exponential form, that square root is going to become a 1/2 power since my index is 2. And that's taking this conversion from the square root over to the 1/n power. I can just rewrite the 6 squared. It was underneath the radical, which means it's still inside this exponent. Then from properties of exponents, which is why we spent so much time on them in 7a, we know that we multiply these. 2 times 1/2 is equal to 1, so I end up with 6 to the first power. That's actually really why the square root and the square cancel. Now we just say it, but why it happens comes down to 2 things. Because I can convert between radical and exponential form, and then also because we can use our properties of exponents, and if I have a power to a power, I multiply them, so I end up getting 2 times 1/2, which ends up just getting me an exponent of 1. What we're going to do in these next couple problems is just practice converting back and forth. How do I go from one form, sorry you guys, how do I go from one form to the other? So we're going to practice going from radical form to exponential form, and then exponential form to radical form. Now there will be some of these that will simplify a little bit more, because if we have some perfect squares or perfect cubes, we want to simplify them as much as possible. So let's look at our first set of examples. They say, convert the following from exponential form to radical form. So I'm starting with something that has an exponent, and I want my final answer to be this radical form. So I want to end up with either a square root, cube root, fourth root, fifth root, etc. Some type of radical in it. And if possible, we're going to simplify. Well, you'll see on all of these we have variables. So we're not going to be able to simplify the variables, we'll just be rewriting them. But if we have any coefficients, we're going to see if we can simplify them anymore. So let's look at example 9. In example 9, this says x to the 1/3 power. So we're starting over here in exponential form. So remember, our denominator of our fraction is our index. So what that tells me then is in example 9, our index is equal to 3, since I have a 1/3 as my exponent. I can rewrite this in radical form by, instead of having the 1/3 exponent, I can replace that with a cube root. And since the x was the base of the exponent, the x then becomes the radicand, or the stuff inside the radical. And that would be our final answer. So we're not solving in these, we're just rewriting them from one form to the other. Let's look at example 10. So example 10 says 4 times y to the 1/5 power. Now the first thing you should ask yourself when you have coefficients is the coefficient being raised to the power, or is only the variable being raised to the power? So what do you guys think here? Is both the 4 and the y being raised to the power, or is only the y being raised to the power? In example 10, only the y is being raised to the exponent because there is no parentheses around the 4y. So since there's no parentheses, that means that only the y is being raised to the exponent. What that tells me then is that in my final answer, I'm going to end up with 4 times something else. And let's look at what that something else will be. So the y to the 1/5, we're going to have to rewrite as some type of radical. We need to know what our index is. What would your index be in example 10? Our index is going to be 5, since it's the denominator of our exponent. So I end up with the 5th root of y. And then the 4 was a coefficient, so it's now 4 times the 5th root of y. I think it's very helpful to write this in parentheses just so that it's very clear that that 5 is your index on the radical. And we're done with example 10. We couldn't simplify 4 anymore because this is just 4 to the first. Let's look at example 11. So example 11 says 16 times a all to the 1/2 power. So we can see here that this is different because the 16 times a is inside parentheses, which means everything is going to end up inside of whatever radical we have. For me to figure out what type of radical it is, I need to know what my index is. What is your index on example 11? Our index here is 2 because that's our denominator of our exponent. So I have a square root. Remember, when our index is 2, we don't tend to write the 2, so it's implied there. 16a was our base, which means it's now my radicand. So I ended up with the square root of 16a. This is one of those examples where we have to think if we can simplify it. So I know the a can't simplify since it's a variable, but can I simplify the 16? So is the square root of 16 able to be simplified? What do you guys think? Yes, I can simplify the square root of 16. The square root of 16 is going to be 4, so I would end up with 4 times the square root of a. So this is a similar property to what we did up above, where I can break this apart into the square root of 16 times the square root of a, and we know that the square root of 16 is equal to 4, so I end up with 4 times the square root of a then on the outside. Okay, let's look at example 12. So example 12 looks a little funky. We have b to the 4 over 5 power. So I'm going to rewrite this as 4 over 5, and let's look at each one of these pieces because they each mean something different. So one of these is going to be the index, and one of these is going to be the power that I'll have on my base. Which one do you guys think is the index? So the index, remember, is our denominator, so our index here is going to be 5, which means we will end up with a fifth root of something. The 4 is going to be a power. So I end up with b to the 4th power inside the 5th root. And because I can't simplify that anymore, I am good to go there. Another way to think about this 4 over 5 is, let's rewrite this. So I have b to the 4/5. Well, I could break this apart as b to the 4th all to the 1/5 power. Let me erase that line so that we have space. So b to the 4th all to the 1/5 power. Because remember, when I have exponent to exponent, I multiply them, and 4 times 1/5 is equal to 4/5. So I'm kind of undoing the multiplication there and factoring it out. So I have 4 times 1/5. We then know that the 1/5 is the same thing as the 5th root, and then we end up with the 5th root of b to the 4th. And that, with that extra step in there, that might be a little bit easier to see. Okay, let's look at 13. So 13 says 6 times x to the 5/8. So we have a coefficient, so we have to make sure, is that coefficient being raised to the exponent or is it not being raised to the exponent? In this case, the 6 is not being raised because there is no parentheses. So the 6 will just kind of be part of my final answer. I'll get 6 times something. And we're going to figure out what that something is. So let's look at the x to the 5/8. So when I rewrite it, which one of these is our index and which one is our power? So remember, our index is the denominator, so our index is equal to the 8, and our power is going to be the 5. Off on the side, if I were to rewrite this and do our extra work that we did up above, I could rewrite this as x to the 5th all to the 1/8. And then we can see from there that our 8 is really our index, since I have 1 over 8. That then translates into the 8th root, and then the x to the 5th is on the inside. Because we had the 6 in front, my final answer would be 6 times the, not the 5th root, the 8th root. Typo. 8th root radical of x to the 5th. I barely left myself enough space there. So 6 times the 8th root of x to the 5th will be our final answer. Sorry, that one got a little messy. Okay, let's look at our last example of this type. So in all of these examples, we have gone from exponential form to radical form, meaning all of my answers have some type of radical in it. We had a cube root, a 5th root, a square root. Example 12 was another 5th root, and then we just had an 8th root. So the first thing I have to notice is I have 2 times x all to the 3/2. So this is one of those cases where the coefficient is inside the parentheses, so that means that the 2 will end up inside my radical. Our exponent here is 3/2. So which one is the power and which one is the index? The 3 is our power and the 2 is our index. So when I go to rewrite this, I have the whole 2x to the 3/2. This will be equal then to 2x to the 3rd, all to the 1/2 if I peel that apart. Now 2x to the 3rd, we can simplify a little bit more, and let's focus on how we can simplify that, and then we'll go back to the 1/2 power. So remember, when I have 2 different bases, I can distribute that exponent to each, and I'd end up with 2 to the 3rd times x to the 3rd, and then I still have all to the 1/2 power from there. We can simplify this a little bit more. 2 to the 3rd is equal to 8, and then I have 8x cubed, all to the 1/2. Now we know that the 1/2 power, that means that I have a square root, so I could rewrite this as the square root of 8x cubed by replacing the exponent to the radical form. The last thing I have to worry about in here is we're all to radical form, that's good, but can I simplify the 8 anymore? So the square root of 8, it's not a perfect square, but can I simplify it more? What do you guys think? I could simplify it more. The reason being is if I write a factor tree on the side, 8 factors is 4 times 2, and we know that 4 is a perfect square, which means the square root of 8 would be equal to the square root of 4 times 2, which I could then take the square root of 4 times the square root of 2 separately. The square root of 4 is equal to 2, and the other 2 is left inside. What that tells me here then is I can simplify this 8, and this becomes 2 times the square root of 2x cubed. Now all of a sudden I started right on the side, so my final answer I'll put up here is 2 times the square root of 2x cubed, all inside that square root. The reason we kept going here was that 8 does have a perfect square inside of it, since 8 factors is 4 times 2, and 4 is a perfect square, which is how we got this 2 on the outside, and then the extra factor of 2 from the 8 is what is left inside. Okay, let's look at our other type. What if we want to go from radical to exponential form? So in 15, 16, 17, and 18, you can see we have radicals in each one of these, and we want to rewrite them so that they look like 9, 10, 11, 12, 13, or 14, where they have just the exponent, so no more radical. So just like before, let's figure out what our index is. That's going to be the key to be able to rewrite all of these. So what is your index in example 15? Our index in example 15 is going to be 5. Remember, it's that superscript in front of the radical sign. So I could rewrite this 5th root as the 1/5 exponent. The b to the 3rd, since it was inside the radical, is now the base. The last thing I have left to do is if I have exponent to exponent, I can multiply those and I get b to the 3/5. I don't have anything else to simplify since I had no coefficients. Let's look at example 16. So in example 16, we do have a coefficient. It's the 12, but the 12 is in front. It's not inside the radical, so the 12 is never going to change. I can just go ahead and rewrite it, and I'm going to just leave a bunch of space inside parentheses to figure out what's going to go in there. So we have 12 times the cube root of x to the 4th. So what's our index this time? Our index is going to be 3, which means I could rewrite this as the 1/3 as the exponent, and then the x to the 4th will be inside that exponent. Again, the 12 is staying off on the outside since it was not under the radical to begin with, so it can't be inside of the 1/3 exponent then. From here, the last thing I can do, power to power, I can multiply them. 4 times a 3rd would give me 4/3. So I get 12 times x to the 4/3 as our final answer. Okay, let's look at example 17. So in example 17, we now have a number that's inside of the radical. So we might have to worry about simplifying it, but let's first convert to exponential form. So in this case, what would our index be in example 17? Our index is going to be 2. Since I don't have a superscript written, we assume that it is a 2 since this is a square root. So I could rewrite this all as stuff to the 1/2 power. Inside of that, I have the 4y all to the 5th. So make sure those parentheses around the 4y got rewritten again since they were there to begin with inside. From here, we know that we can multiply the 5 and the 1/2, and this becomes 4y all to the 5/2 by multiplying our exponents. This is the part where we have to see if we can simplify more. So when we had two different bases inside raised to a power, remember we can distribute that power, and this will become 4 to the 5/2 times y to the 5/2. Y to the 5/2 we can't simplify anymore since it is already in exponential form and our base is a variable. Now the 4 to the 5/2 we want to see if we could simplify. The way we're going to see if we can simplify this is looking at that index and looking at our base. So our index is 2, which is the same thing as a square root, and 4 is a perfect square. So if I rewrite this back in radical form, so I'm going to actually go backwards for a little bit and rewrite this as a radical, I would get the square root of 4, then I would have the 5th power out on the outside. So what I did right here was I used the 5/2, and that denominator being a 2 tells me that I do have a radical. That's an index of 2, so a square root. So I end up with the square root of 4, and then the 5th power is still there. It hasn't gone away. We know what the square root of 4 is. That's a perfect square, so I get 2, and then the 5th exponent is still there. So is the y to the 5/2. Then from there, 2 to the 5th, I can multiply out, and I would get 32 y to the 5/2 still. And that would be our final answer then on example 17. So we got to be careful with those coefficients and just make sure we simplify them all the way. Okay, let's look at example 18. So in example 18, we have the cube root of 27d to the 5th. So this is similar to 17 because both the 27 and the d to the 5th are inside this cube root, but the difference here is that there's no parentheses around the 27d, which means only the d is being raised to the 5th power. So when I go to write this in radical form, I know my index is 3, and this will get rewritten all to the 1/3 power, but I'll end up with 27d to the 5th. I won't need extra parentheses inside because the 27 is not being raised to the 5th power. This is where we do want to distribute to each piece again to see if we can simplify. So I get 27 to the 1/3, d to the 5/3. 27 to the 1/3, it's easier to look at it from radical form, so I'm going to rewrite this as the cube root of 27. Whoops. Erase that. 27. There we go. Cube root of 27, and then the d to the 5/3 is still on the outside. Let's get a little bit more space. Now the cube root of 27 is a perfect cube. We had done that earlier in example 4, and the cube root of 27 is equal to 3. So I get 3d to the 5/3. And so that cube root of 27 we had already done earlier. That was back in example 4, if you want to see the work that goes with it. And that is our last example on learning target 7b. So 7b, we talked about how to go from exponential to radical form and how to simplify lots and lots of square roots, cube roots, and fourth roots.